This video is a step-by-step solution for the example entitled Evaluating Work and Heat Transfer for an Internally Reversible Process of Water. In this example, you will learn about analyzing an internally reversible process for water in a closed system undergoing a phase change from liquid to vapor at constant pressure due to heating. In this example, you will learn to compute the work and heat transfer for this process. Let's look at the problem statement as given to us. Water, initially a saturated liquid at 150 degrees C or 423.15 Kelvin, is contained in a piston cylinder assembly. The water undergoes a process to the corresponding saturated vapor state, during which the piston moves freely in the cylinder. If the change of state is brought about by heating the water as it undergoes an internally reversible process at constant pressure and temperature, determine the work and heat transfer per unit mass, each in kilojoules per kilogram. First, let's do a critical read of the problem statement, highlighting in red the important information given and in green the information requested. Highlighted in red for the information provided, we have the following. Water, initially a saturated liquid at 150 degrees C, is contained in a piston cylinder assembly. The water undergoes a process to the corresponding saturated vapor state, during which the pistons move freely in the cylinder. If the change of state is brought about by heating the water as it undergoes an internally reversible process at constant pressure and temperature, and highlighted in green for the requested information, determine the work and heat transfer per unit mass, each in kilojoules per kilogram. Let's start to develop the solution. The first thing we have to do for any problem solution is to summarize what is known. This is essentially the same information we highlighted in red in our critical read of the problem statement presented here in the bulleted list. Water contained in a piston cylinder assembly undergoes an internally reversible process at 150 degrees C from saturated liquid to saturated vapor. The next thing to do is to summarize what we have to find. This is again the same information we highlighted in green in our critical read of the problem statement, presented again as a bulleted list. Determine the work and heat transfer per unit mass. The next step in the solution is to develop a relevant schematic. In this case, it was provided to us. However, let's highlight a few important pieces of information that were provided, which will help us develop our solution. The first thing to note is that there is no mass entering or leaving the piston cylinder assembly. This immediately suggests that a closed system approach is the correct one. Having recognized this important fact, let's select our system boundary. In our case, it is selected to enclose the water in the cylinder and follow the physical boundary of the piston cylinder assembly, as delineated in the schematic by a red dashed line. The next step is to develop the appropriate thermodynamic diagrams to represent the process as requested. The PV diagram, showing the vapor dome. State 1 is a saturated liquid and its saturation temperature is given to be T1 is equal to 150 degrees C. The process from 1 to 2 is a heating process at constant pressure, hence P1 is equal to P2 and T1 is equal to T2 during the phase change. The process is represented by an horizontal line on the PV diagram until we reach the saturated vapor state at the right edge of the vapor dome. Note that the specific volume increases during the process. The work per unit mass for this internally reversible process is the area under the curve. And now the TS diagram is shown on the right. Again, the process from 1 to 2 is a constant temperature process during the phase change. Note that the specific entropy change is positive during this process. The area under the curve represents the heat transfer added during this constant temperature process. The next step is to develop an engineering model, which is a set of simplifying assumptions which will allow us to perform the analysis of the problem. The water in the piston cylinder assembly is a closed system. The process is internally reversible. The temperature and pressure are constant during the process, and there is no change in kinetic or potential energy between the two end states. Having completed all the preliminary steps for our solution and represented the processes on the PV diagram and TS diagram, let's develop the rest of the analysis. In determining the work per unit mass during the process, since the piston is the only work mechanism and the internally reversible process operates at constant pressure, we can express the work for the whole process as W over m is equal to the integral from 1 to 2 of PdV equal to P times V2 minus V1. With values from the saturated vapor table at 150 degrees C, where V1 is equal to 1.0905 10 to the minus 3 cubic meter per kilogram, and V2 is equal to 0.3928 cubic meter per kilogram, the work per unit mass is obtained as follows. Note the conversion from bar to pascals or Newton per meter squares, joules to kilojoules, to calculate the work per unit mass in kilojoules per kilogram. This is the answer for the work per unit mass for the entire process, which is the first answer we were seeking. The positive sign indicates that the work is done by the water on the piston. In determining the heat transfer, we first apply the equation for the internally reversible heat transfer at constant temperature, which is as follows. Written both in terms of the extensive property, capital S, or the specific entropy, small s, times the mass. Dividing by the mass, we get an expression for the overall heat transfer per unit mass. Q over m is equal to T times S2 minus S1. With values from the saturated vapor table at 150 degrees C, where S1 is equal to 1.8418 kilojoules per kilogram Kelvin, and S2 is equal to 6.8379 kilojoules per kilogram Kelvin, the heat transfer per unit mass is obtained as follows. The heat transfer per unit mass for the entire process is then evaluated to be Q over m is equal to 2114.1 kilojoules per kilogram, which is the second answer we were seeking. The positive sign indicates that the heat is being transferred into the system. As shown in the PV and TS diagrams, the work and heat transfer can be represented as the area under the curve in those diagrams. The heat transfer can also be evaluated from an energy balance written on a per unit mass basis as U2 minus U1 equal Q over m minus W over m. Substituting W over m equal P times V2 minus V1 and solving the equation above, we obtain the following. Q over m is equal to U2 minus U1 plus P times V2 minus V1, which can be rearranged as follows. U2 plus PV2 minus U1 plus PV1, or equal H2 minus H1 by the definition of H is equal to U plus PV. From the saturated vapor table at 150 degrees C, H2 minus H1 is equal to 2114.3 kilojoules per kilogram, which agrees with the value of Q over m we obtained previously in our solution. Quick quiz. If the initial and final states were saturation states at 100 degrees C, 373.15 Kelvin, determine the work and heat transfer per unit mass, each in kilojoules per kilogram. You may want to pause the video at this point to work out the solution before proceeding. The answers are W over m equal to 170 kilojoules per kilogram and Q over m is equal to 2257 kilojoules per kilogram. Hopefully, those are the answers you calculated. If not, you may want to review the various steps in this video and check your calculations. If you still are not able to get the correct answers, here are a few hints. From the temperature table of properties of saturated water at 100 degrees C, P1 equal P2 equal 1.014 bar, V1 is equal to 1.014 10 to the minus 3 cubic meters per kilogram, and V2 is equal to 1.673 cubic meter per kilogram. and S1 is equal to 1.3069 kilojoules per kilogram Kelvin, and S2 is equal to 7.3549 kilojoules per kilogram Kelvin. The expressions and calculation for W over M and Q over M are identical to what was done earlier. Substituting the numerical values above in the expression is left as an exercise. In closing, in this example, we have learned about analyzing an internally reversible process for water in a closed system, undergoing a phase change at constant pressure from liquid to vapor due to heating. We also learned how to compute the work and the heat transfer for this process. This concludes the step-by-step solution of the example entitled Evaluating Work and Heat Transfer for an Internally Reversible Process of Water.